In Unit 5 of AP Chemistry's Kinetics unit, the final section, topic 11, is called Catalysis, which is basically using a catalyst in a reaction. So what we're going to cover is what is a catalyst, how does it change an energy profile, how does it show up in a mechanism, and how do you write the rate law if it is involved in the mechanism in the rate determining step, and how does it change the Maxwell Bozeman distribution, or what changes on the Maxwell Bozeman distribution. So those are the top 4 ways that a catalyst will show up in content or in questions on the AP exam. So the first thing is, what is a catalyst and how does it alter the reaction rate? So what a catalyst does is it increases the rate of the reaction, so it increases the rate of a reaction. It's like the opposite of an inhibitor. An inhibitor decreases the reaction rate. We use that a lot in our foods with preservatives. Increases the reaction rate, or increases the rate of reaction. It does not produce anything more, though, so be really careful. These are the things that make sure that you write these down. I'm going to put it above. It does not change the enthalpy. So don't try to have somebody talk you into that. It makes it more exothermic or more endothermic. So enthalpy stays constant. The other thing later on in a unit coming is the equilibrium constant called capital K, not lowercase k. The equilibrium constant, and this is in Unit 7 coming. So the equilibrium constant, that also does not change. So it just increases the rate of the reaction by allowing the particles, the reactant particles, so the reactant particles, they'll call it an alternative pathway. And one of the examples I've used in the past is it's almost like an expressway around a big city, is that if that expressway is open, you can take that alternative pathway and it should allow you to get to where you're going faster, but not, you didn't get there, like more. So again, the destination stays the same. So again, our reactant and products are still the same. It's just an alternative pathway. Okay, there are 2 types of catalysts. One's called homogeneous and one's called heterogeneous. The easiest definition of the difference of these is a homogeneous catalyst has the same, what's called state of matter, meaning solid, liquid, gas, same state of matter as the reactants. The other thing about it is this just allows, again, a lower activation energy. And that's what we'll talk about when we get to the graph, is that it does give a lower activation energy. It gives an alternative activation energy pathway. And it allows there to be a different way to get to the products, but that just uses less energy. The heterogeneous catalyst is a different state of matter as the reactants, okay? But the other thing about a heterogeneous catalyst is that it may affect 2 different things, or one or both, okay? The other thing it will do is always going to give you a lower activation energy. It's called an EA cat. But it also could help you with the orientation of the molecules colliding. So it could also help with the orientation of the particles for an effective collision. So it could also affect both. So again, this could have a two level effect. It could affect the activation energy, of course, but it also could help with the orientation of the particles and allow them to react more efficiently. Because remember, there's 2 things that particles need to do. They have to collide, of course, but they have to collide with the right energy, and they have to collide with the correct orientation for a collision to be effective. And a heterogeneous catalyst could affect just both of those. Okay, so those are our 2 types of catalyst. All right, let's move on to then how does this change the energy profile? So what will happen with the energy profile? I'll start with the 2 on the left. So again, we have an exothermic and an endothermic profile. Take a look at those. So again, we have this one here versus this here. Again, think about which one was which. I have three separate videos on this. One is about energy profiles. Then another one is about multi-step profiles. And so you can review those if you need that. And that's the change in enthalpy. And then how does a catalyst affect this? So what a catalyst does, let's actually use red. It creates an alternative pathway like that. So you'll see that on the AP exam, or you'll have to draw it yourself. So then this is the new activation energy, EA with a catalyst, whereas before the activation energy went from here to the top, okay? So again, this is where that transition state is, and then you have an activation energy of the reaction without having a catalyst. Same thing here, the activation energy is from here to here without the catalyst, but if you add a catalyst, so this could be either an endothermic or exothermic reaction, and now the activation energy just is from here to here. And then again, you'd say EA and then CAT, like for catalyst. So again, it does not change the enthalpy difference. It also does not change where the reactants and products are either. So again, we still have our reactants here, our products here, a transition state here, or activated complex, reactants here, products here. And then again, this would be the transition state up at the top. All right. And then again, just to not make sure you're not misled here, the orange line is the activation energy. So I'm just going to label that a little bit better. So this right here is the activation energy without the catalyst. Okay. All right. Then the other thing that can happen is a catalyst could create like a multi-step reaction. So it could go like that, and then maybe even have another step and then come back down. So that is possible that a catalyst could create an alternative pathway that then has like an activation energy 1 and another activation energy, and then this first one would be called EA1 with a catalyst, and then the second one right here would be called EA2 with a catalyst involved. But in reality, what really matters again is that the first one is larger than the second one, so then that would again be what's called that rate determining step. But it doesn't change again where the reactants are, where the products are, where the transition state is, and it also does not change again the fact that this is a negative delta H, or enthalpy of reaction that is exothermic. So I'm just going to write that again one more time. So this does not change that number is negative, and that this is an exothermic reaction. It just allows an alternative pathway, and sometimes it'll have maybe even have its own mechanism. So that's what leads us into the next example that I'm going to do is with the destruction of the ozone, with chlorine being what's called a catalyst. So we'll talk about how is chlorine a catalyst, how does it show up in the reaction, and how does it take maybe this one reaction that used to maybe have like, you know, an energy profile like that, and then how does it turn it into a reaction that actually has a multi-step profile with two elementary reactions in that overall reaction for the ozone. All right, so the next thing would be how does a catalyst show up in a reaction mechanism? And what you're looking for here is that it's something that starts in step 1 and is reformed in step 2. So as you look for what is it, so it is a reactant in the step 1 or in the beginning, and is reformed as a product. And I'm going to run out of room, so I'm just going to say it's reformed as a product in typically the last reaction. So usually these only have 2 steps, so it's usually in step 1 it's a reactant, and then step 2 it's a product. So that's how you'll determine if it is a catalyst versus an intermediate. Don't get confused. I'll circle the purple here. This is our intermediate. The chlorine monoxide is actually an intermediate. Whereas the chlorine is our catalyst. And then the other thing you could do is still check, you know, how does it show up when you put these together. So what will happen is you'll bring down then, I'll just kind of circle, you'll bring down the ozone and then this monatomic oxygen. And this again is how do we know if this reaction mechanism is valid? The 2 steps in this case have to sum up to the overall. And then we do get 2 oxygens as products. So our first, I'm just going to kind of do this again. Our first check, and this is in a previous video to see if a reaction mechanism is valid. Our first check is that we have met requirement 1, which is that the 2 reactions put together sum up to be the same as the overall reaction. And then the other one would be, can we write the rate law for the slow step? So in this case, the slow step is going to be the one that has the catalyst in it. So I'm just going to erase that now. And that's the one that we're going to use to write the rate law. So for that one, the elementary reaction, here I'll actually put it in red. So the rate law for this second step, using what's called the molecularity that I had in a previous video, is going to be, yes, it will have the catalyst in it. That's new. We can't have an intermediate in a rate law, but you can have a catalyst in a rate law. And so that would be the rate law that would be kind of like predicted or expected. And then if they told you that was the experimentally determined rate law, then you would argue that, okay, number two, the second step is that the experimentally determined rate law matches the rate law of the mechanism. So if they did tell us that that is the rate law, then we're good to go. And you'll notice that it does not include the ozone and the oxygen in the rate law. That step is fast, so that's why this step is not included in writing the rate law. And then again, the intermediate is never going to be in the rate law. So right here, the intermediate is never going to end up in a predicted rate law. All right, last but not least, how does it affect the Maxwell Bozeman distribution? So for the last thing is going to be, well, what happens to this graph? And usually Maxwell Bozeman distribution is covered with gas laws. And so you may have learned that like the activation energy might be here, and then all of these particles, it's called area under the curve. So this is called the activation energy of the reaction without a catalyst at this point. So that's the activation energy, and it's the minimum energy. So I'm just going to kind of zoom in here. It's the minimum. So it's the minimum energy needed to break the bonds. Now, they still have to have the correct orientation. I'm going to keep saying that. They still have to have the correct orientation, but it is the minimum energy needed to break the bonds. And so all of these particles, whatever number this is, you actually could use like a calculus formula to figure out what amount that is. That's how many particles will have the energy needed to react with the correct orientation still, and then the reaction will occur. So what's kind of cool about a catalyst is it lowers the energy. So like right here is the minimum energy needed, and you catch all of these particles, and all of these still get to go also. So now you have a larger amount of particles that have the appropriate energy to break bonds. So this again is the activation energy with a catalyst. And again, what a catalyst does is it gives an alternative pathway. That's the way to say it. But the big thing the catalyst does is it lowers the activation energy required for the bonds to break. And so now we have more particles with what's called sufficient energy. So we have more particles. I'm just going to rewrite this again. So more particles with sufficient energy to break bonds and react. They still have to have the correct orientation, but we now have more of them that have the right amount of energy. Now, a catalyst again could help with the orientation, but that just depends on the type of catalyst and the type of reaction if that happens besides. All right, so there is our last section for Unit 5. Congratulations, you've made it through a kinetics chapter, which is typically a brand new content for a second-year chemistry student or a college-level chemistry student. And I hope that this information was helpful to see the 4 different ways that a catalyst can alter different factors in the kinetics chapter.